So we have another talk now from Henning, who's relocated to the garden. And dear audience, you've seen Henning yesterday, but for those of you who have not been here yesterday, I would like to present him once again. So Henning has been a hardware hacker since his childhood, but gained interest in wireless communication during his Diploma and PhD studies in information technology at the University of Bremen. And having left academia for the industry a few years ago, Henning decided to intensify his free time activities on software-defined radio and is currently waiting for his amateur radio novice license examination to be finally able to transmit and not be restricted to receiving only. Well, that's about Henning. So our speakers just before are actually a good example of what we've done together with the academia, and I think this is a very, very good example that there is a strong cooperation with students and PhD students, and that we're giving students and PhD students and also research a space to present projects and to interact. And as I mentioned yesterday in the very beginning, I'm also very glad and very happy that we have that very good and very fruitful cooperation with the European Radio Days and with you, Jean-Michel, and your colleagues particularly. So here this talk is going to be about bridging the gap between scientific SDR and amateur radio. So there is kind of a gap, and this is also the reason for us being here and the reason for the existence of the SDRA. And in the introductory slides, Jean-Michel, you wrote also that this is also one of the important ideas why the European Radio Days came into existence. So that's generally a good point for us to be around, and Henning made up his mind a little more into this direction, and for that reason I would like to hand control over to our video team and to play the pre-recorded video. Please, video team, go ahead.
So thank you very much for the kind introduction. Welcome to my talk today. My name is Henning Paul, and I will tell you a little bit about scientific uses of software-defined radio from a perspective of a former scientist at a university. So what will I be presenting today? First, I will give a short introduction, and then I'll go into the technical details. So what's the difference between software-defined radio and, let's say, scientific communication demonstrators? Software-defined radio has been used by hobbyists for like 10 years, approximately by now, at least in the mainstream. This was the advent of the RTL SDR, which was the major breakthrough for software-defined radio for hobbyists. But actually, the concept of software-defined radio is known longer, for at least the 1990s, but back then it was only used in research and development. So means big communication companies, for instance, and also the academia, means universities and research institutes used software-defined radio techniques that you would call software-defined radio today, but usually go by the name of communication demonstrators or hardware demonstrators or the like. Back then, this was a very costly thing to do. You needed very expensive hardware, and because of that, universities often resorted to own designs. They designed their own transceivers and signal processing devices and such. And what I would like to tell you today is what was used in the 2000s at the Department of Communication Engineering, the ANT at the University of Bremen. I was a researcher there for 11 years in total, and I had to do with, yes, actually all of these hardware demonstrators that I will be showing today. I used those more or less intensively. So that's why I would like to start with the first system. And I'd like to give you a quick motivation on what was the purpose of hardware demonstrators. And actually, there, of course, was always a desire to evaluate communication algorithms that had been developed in industry or in academia under somewhat realistic channel conditions, means propagation conditions, and also include all the hardware non-idealities that you usually have. And that's the reason why we did all this stuff back then. And topics that were of particular interest back then were in particular OVDM, CDMA, and very exciting topic, multiple antenna systems. And of course, as a researcher, the question is what frequencies should you use for your studies? And the best solution would have been communication bands like 2G or 3G bands. But what usually was common practice back then is that you use the 2.4 gigahertz ISM band. Of course, this is only a semi-legal solution because you can't really use the totally legally these bands, but usually when you resorted to low transmit powers, well below powers that were usually used for Wi-Fi systems, you wouldn't run into problem by doing so. So the first demonstrator that was developed at the ANT was a single antenna hardware demonstrator, which was the result of a diploma thesis around 2000. There were two incantations basically of the system. There is the modular version that's shown here in the middle of the picture, and there's the standalone version with some user interface, which is basically both the same technology. I would like to concentrate on the middle one here, how this looked like and what the capabilities of the system were. This was a modular system, means the baseband interface and the transceiver were separated, and they were interfacing with each other using SMB connectors. So it means the baseband was the analog baseband was the, say, division line between these two devices, two systems. And this was a project by a former colleague of mine, Thorsten Hase. He did all this as a diploma thesis in 2000, and of course he had support by our lab engineer Heinrich Masemann, Delta Bravo 7 Bravo Papa, and it was more or less a joint project of these two guys back then. So what does this system contain? How does it look like technically? So first, we look at the modulator-demodulator unit. Maybe this is the part that's more interesting to the ham radio operators. This system, this module used an Harris chipset, which was usually originally designed for Wi-Fi 11.B, and consisted of 3 chips, which is the main IQ modulator, external VCO. This one modulated onto intermediate frequency, and then there was the mixer that actually did the up conversion then to 2.4 gigahertz, and a power amplifier chip after the mixer. And we had this neat little case here, with some rudimentary user interface. You could just select one of 4 channels and toggle between TX and RX. This was a half duplex system. Then we had the analog baseband interface here, which would then interface with the next device that I will show in the following, which was basically this one here. This is the core of this device is in Xilinx FPGA, Vertex E FPGA, with static RAM as a FIFO, and some interface chip, CPLD, that was used for the parallel port interface. You might smile a bit, but back in 2000, the parallel port was still, for most applications, the port of the interface of choice. USB was just new back then, so a lot of systems used a parallel port back then as an interface. Yeah, attached to this FPGA were AD converters and DA converters, just like you would do it today. Yeah, it's not a difference. So today you would do it exactly the same. Here we have parallel DAC and parallel ADCs, dual channel DAC, and two single channel ADCs that did the digital to analog or analog to digital conversion, vice versa. And we had a clock generated chip on this device, which is not that different actually from the famous SI5153, or the other way around. I can't remember that. It's a clock synthesizer that's ubiquitous in every today, more or less in every application today. And this was an, say, early predecessor from a different company that did basically the same, synthesizing the sampling frequencies with some digital interface. Yes, I guess SPI or I2C or something like that. Yeah, and then on the PC side, we had this little graphical user interface that Thorsten wrote back then, which, transferred binary files, IQ files, containing the samples to transmit, or vice versa, the received samples over the parallel port. Yeah, just byte-wise, and then filling the FIFO of the baseband board by doing so, or the other way around, transferring the IQ samples from the FPGA's RAM buffer, the static RAM buffer, into the PC. And it's more than 20 years old, this technology, but I guess not that different to what you are doing today, for instance. Yeah, and what could you do with this kind of device? And you could, for instance, implement a GSM transmission. You know GSM 2G mobile phone system, mobile communication system. And what other colleagues of mine did back then is implement all the physical layer of GSM, the GMSK coding, and the forward error correction, and the synchronization, and the channel estimation, all the like in MATLAB, and then used the parallel port to upload then a frame, a communication frame, into the transmitter, and transmit it and receive it vice versa with the corresponding receiver, and then have it offline processed then in MATLAB and at the receiver side. And back then we used these demonstrations often in the lectures to show the students how a practical communication system would operate. For instance, here in this picture, you see the complex envelope of the transmit signal. It's GMSK, so that's why it's a circle. And then, for instance, you could have a look at the transmit spectrum. I guess the power spectral density of the transmit signal, the time domain signaled at the receiver side. Then, for instance, the result of the channel estimation in the Z domain, as well as in frequency domain, and the impulse response. And for instance, also the impulse response over time, which is of particular interest, because when you're doing mobile communications, usually you have fading channels, meaning the channel vary over time. And you could use back then, 20 years ago, the visualization features of MATLAB to illustrate how the impulse response would behave over time. Or here in this case, the frequency response. You see the notches there from multipath propagation, the zeros in the frequency response, and how these would then change over time. This is what the colleagues used back then. Another application was Hyperlan 2. Hyperlan 2 is what later became 11.A Wi-Fi. It's Hyperlan 2 was the OC part. It's not an IEEE standard, it's an OC standard, and it never actually was accepted in industry, but the technologies were then later used in 11.A and then also later in 11.G. It's an OFDM-based Wi-Fi system, and the colleagues wrote a demonstrator in MATLAB to transmit these OFDM frames. Here you see, for instance, I and Q and time domain at the transmitter side, and here the typical OFDM spectrum of one of these frames. Think of 11.A or 11.G Wi-Fi frames in this case. And then the whole transmitter was implemented to be operated then in non-real time. And yeah, this is, for instance, the output of the cross correlator, which does the time synchronization. And for instance, this is the receive spectrum and the result of the OFDM channel estimation. Yeah, you can nicely see all the individual subcarriers and how they are attenuated by the actual frequency response. Yeah, and for instance, in the end, the constellation that results then from after the equalization of the OFDM transmit frame. Yeah, so this was 2001. This demo. This was basically when I joined the university. This was what the researchers back then showed to the students, for instance, the first semester students, as a teaser of what is actually done in the Department of Communications Engineering. Yeah, then only 1 or 2 years later, then multi-antenna systems became big in research. Means using multiple antennas at once, both for transmission or for reception, in order to do fancy stuff. And that's why the colleagues decided to extend the system to a multiple antenna systems. And this was the result then back in 2002. This is basically the system you saw before, using 8 coherent channels. Yeah, all the channels are fed from the same local oscillators. They are synchronously digitizing the ADCs. And yeah, this was a very, let's say, groundbreaking thing, because there were not many universities in Europe that had something like that, demonstrator able to do a coherent multi-antenna transmission. And this again was a project by Thorsten and Heinrich, and it's called MASI, yeah, as an homage to Heinrich Masemann, the colleague that our lab engineer. And yeah, it's a refreshed multiple channel version of the demonstrator we saw before. We had different modulators, demodulators. This now is a simplex system. This is not capable of doing half duplex anymore, but this simplified the design significantly. That's why the colleagues used this simplex system. Sampling rates were up to 50 megahertz, so this is quite whopping back then. But of course, there needs to be a drawback. Drawback is this thing only had USB 1.1. Yeah, I guess you remember 12 megabits per second. So this definitely was a non-real-time system, say offline processing, because you would then, at the receiver side, for instance, fill the FIFOs. Yeah, means 1 mega sample per channel, and then you would use the USB 1.1 interface to transfer all the RAM buffer contents into the PC and do the MATLAB processing. And this could take a minute or two. It was not too fast. It was, but it was okay, yeah, for the time being. Yeah? And this is the device that I did a lot of research with. I did my Studienarbeit with this on this box. I did my project thesis on this box, and I also my diploma thesis was heavily supported by measurements done with this box. So this is the one that I can relate with the most, this device. And now a little bit more of technical details on what contains this box. You see, for instance, this is now one of the receiver boards. It's still a Vertex FPGA, and still it's a static RAM that's attached to it, and we still have two separate ADCs, so it's not that different to the single channel version. But what's different is the bus here. Yeah, so this is a 8051 Intel microcontroller bus. So Thorsten and Heinrich decided to use an 8051 with USB 1.1. So this basically, you would then use the 8051 microcontroller bus to transfer all the data. Yeah, and this is what this connector back here, this DIN connector is connecting to. It's an 8-bit parallel bus, straight from the 80s. The modulator, or a demodulator in this case, because it's the receiver board, is directly located here, and you should imagine some like a sheet metal box over here. Yeah? This is just removed for the photograph, so it's properly shielded. We have some shielding cage over the area here. And the block diagram basically directly represents what's contained on this PCB, and you can have a look at the slides then yourself and try to find every device in the block diagram also on the PCB. So next slide. Yeah, now what's the purpose of this box at all? So yeah, you can do MIMO measurements, means multiple input, multiple output, means you transmit over several antennas, you receive with several antennas. For instance, you transmit over 4 transmit antennas and you receive with 4 receive antennas. That means you get 16 transfer functions in total. And you can see these here on the slides. From every transmit antenna to every receive antenna, you have a transfer function, and there are 3 different colors here on the slide. This is just 3 different trials. Yeah? So it means the channel has changed in the meantime. So this is why the channels look a little bit different. And you can see the 16 megahertz of bandwidth, 16 megahertz one-sided. It means 32 megahertz of bandwidth that every channel has here in this demonstrator. This picture is taken from a paper that was written by Jürgen, Delta Charlie 3, Bravo Whiskey, and my former prof, Professor Kammeier, and this was a joint paper in 2003 by these guys. Yeah, we then later did some extensions on this system, and well, here's one more example what you actually could do with this kind of technology. One antenna was transmitting data, and then we have received with 4 different antennas. We get 4 different replicas of the received signal, and on what you see in A is the signal on receive antenna 1, on B is the signal on receive antenna 2, and you see basically you can only imagine that this was a 256 QAM, and by combining these 2 signals with the correct phase shift and correct scaling, you end up with the result here in C. Yeah, I can almost guess that it was some kind of QAM. When you now combine the receiver signals from all 4 antennas, you end up with this signal constellation. Yeah, that means multiple antenna systems, receivers will give you an SNR gain. Yeah, you combine the different replicas of the system, different replicas of the received signals in order to improve your receive SNR. I will give an application to amateur radio in my other talk, so it's a quick just advertisement for the for my other talk where I apply something like that for continuous wave signals. Yeah, extensions to this system. Yeah, we again modded the system into a half duplex system by using some relays and an LO splitter, and also did some measurements. If you're interested in the results, here are the links where you can find the full papers from these results. Yeah, and that's basically what we did with this demonstrator. But of course, over time, you get your, you want more from your hardware, and this is why we moved to a real-time capable system. I will only give 1 slide on this system because this was a commercial off-the-shelf system. We didn't build it ourselves. So this is why I would like just to give a short wrap-up what the system actually, how it looked like. So it was a compact PCI system from the shelf containing ADC and DAC cards with FPGAs. There was a 4-channel modulator-demodulator that would interface with these ADC and DAC cards. And there were also a card with a FPGA as well as a digital signal processor, one where you could also do some real-time processing of received signal on the DSP in connection with the FPGA. Yeah, and it also had the clock source, which was GPS disciplined. This is particularly nice because by doing so, you didn't need to hard sync receiver and transmitter with a cable. Yeah, when you just let both of them synchronize to GPS, and then you have a synchronous system from the transmitter to the receiver. So this is why we also chose the clock source board in this system. Yeah, so this ends my talk. So What did you see today? Yeah, I showed you a little bit on what hardware we used back then in the university for demonstration purposes. And as a teaser, in my next talk, in the follow-up talk, I will show you what I did since then. So the hardware designs I did on my own, which were, of course, heavily inspired from these hardware demonstrators that I've just shown you. So I thank you very much for your attention, and I'm happy to answer questions in the Q&A.
So thank you very much, Henning. Very, very interesting. Once again, all our talks are interesting. Really, very good. Excellent. Well, what I find most interesting about that is that you're demonstrating that you can indeed produce modern digital signal processing electronics yourself, and you can really do that also as a hobbyist, also as a vocational engineer. And you've been doing that. Okay, you have a certain background. You also do that in a professional domain, but it is possible to take schematics from application sheets and put them into KiCad and try them out and get them running. And that's really an interesting signal to the entire community. You can do that. You're not limited to analog stuff, but you can really also do signal processing yourself. You can create PCBs. You can do all those sorts of things, soldering, FPGAs, and so on. This is definitely possible. There are hurdles. It's not super perfectly easy, but it can be done. And particularly in a university environment where you do have prototypes, you don't have a big production of a big series of devices, but also for small amounts of devices. This is definitely feasible also in a financial range which a private person can cover, which is good, which is makes a lot of hope and a lot of it inspires you, inspires many people around there to try out those things themselves. Very good. Okay, thank you very much for this insightful talk. There has been some interaction in the talk. In the chat, but I think these questions were discussed.
Yes, I think it was about the previous talk.
Yes, it was about the previous talk.
It's on the previous talk. Yes, it is. I have controlled it, Marcus. There is nothing now in the talk about Henning's talk.
Yeah, okay.
It was just a historical wrap up. Yeah, so all the new content was in my talk yesterday. This was just an entertainment talk today about what has been what has happened in the history up till now. Because when software-defined radio became big, like 10 years ago, I was very excited because now I could do all the stuff that we've been doing in the lab with rather expensive hardware, now with cheaper cheaper hardware. For instance, I was a lecturer back then. I had a lecture on practical applications of digital communications. And what I did, I ordered just a kit of RTL SDRs, and then we had in my lab exercise, then I made the students play around with these RTL SDRs and try to look around the spectrum and try to find out what kind of signal is this in the spectrum. And I was really excited that, say, this rather niche technology that it was up till then became more widespread then.
Yeah, indeed.
Well, when I remember what I
This
did,
is a good development of the history until now.
yeah, I remember what I did back then. Maybe you've seen that video from who was it? Um, someone who who was using the USRP1 to emulate a GSM base station. I think about 10 years ago, 12 years ago, something like that. And this guy, Christine Patchett. Well, anyway, that time, Chris Patchett was programming a GSM base station. And well, I mentioned earlier here in the stream that I passed my amateur radio license back in 1989, so that's quite some time ago. And that was when I was trained in circuits and oscillators and all those things. And I followed up the development in those past years. And what we've seen, the industry going away from components with a wire at the ends, right? Wired components back to surface mounted devices. And first of all, those surface mounted devices led to a big rupture because many people couldn't do their experiments anymore because soldering was quite difficult and a lot of electronics engineers or vocational hobby engineers turned away from their hobby and didn't do it anymore because, well, they couldn't keep up with the kind of products, parts you could buy, and they couldn't use them. And and about 10 years ago or so, or 10 to 15 years ago, we saw those breakout boards coming up. And many companies were producing little PCBs with little tin patches, whatever, metal patches, where you could solder up your surface-mounted devices, ICs, and so on. And this brought in a lot of new creative people. And at the same time, well, this is analog electronics, but well, electronics in general. But more or less at the same time, we saw those USRPs coming up. And I think with the USRPs, I personally had the impression that there was going, there was opening a door in front of myself, and I was looking into Wonderland, you know, an entirely new field of research and also hobby activities, and well, which wasn't new after all, but it was new to the public, right? We were able to do things once again, and I was very, very happy about that. I mean, remember last year when we had Professor Rode here in the SDRA, and we had him for a very good reason because he was one of the inventors, maybe even the inventor back then, who was one of the first people who thought about not working on currents, but on data streams, and the description of an electrical signal. And so, of course, the industry and parts of the academia were able to handle those things before. But since that time, since about 10 years ago, the public and radio amateurs are able to do this. And I also got in contact with GNU Radio, I think when was that, in 2007, something like that. But in 2006, 7, something like that, I still didn't know, okay, how we're really going to use it, because I didn't see the devices. And I only got to that point when I saw the USRP1, USRP2 coming up, and this was really one of the first really good and really reliable and useful devices where you could generate the signal right out of software and also process signals directly with software. And this was actually one of the one of the reasons for me that I bought the USRP2. And interesting enough, the USRP2 is still a very, very good system and very useful, and it helps me quite a lot to do my own experiments. And of course, later on, I mean, every one of us has a whole collection of devices, and of course, we also every one of us tried out the RTL SDR because it's so cheap, and value for money is really fantastic with a small device, and you can do wonderful things with it. And that's also my recommendation to everyone, to start with it, because yeah, sure, I know. So there is a path into software-defined radio for every one of us here, and all the audience who are watching, using these devices that are becoming ever cheaper, like the HackerF and the Lime SDR and the Pluto, Adelm Pluto, and so on and so on. And well, you can have a lot of fun with those devices for sure. So yeah, we have another talk pending.
I should say many thanks to Henning Powell for his both contributions to this conference. And
You're welcome.
So have a nice afternoon. I see you are sitting in a sunny garden, and I would like to sit there as well.
Well, but Michael, you're sitting on a beach.
Yeah, that's my green wall.
Yeah, Henning, a big thanks from me also.